Welcome to The Explainer. Today, we're going to dive into a fundamental truth of modern software. Building systems that span multiple computers is just profoundly, fundamentally harder than building for just one. And we're about to find out why. This clever riff on a pop song? It just perfectly captures the messy, unpredictable, and sometimes chaotic world of distributed systems. It's a world where absolutely nothing is guaranteed. So let's unpack what that really means. Okay, so our first step here is to completely shatter a core illusion we all have about computers. We like to think of them as these perfectly predictable machines, but as you're about to see, the moment you connect them together, that illusion of control just breaks apart. So on the left, you've got the simple world of a single computer. It's straightforward. It either works or it crashes. It's an all or nothing deal, right? But on the right, in a distributed system, something way more sinister happens. Some parts can fail, while other parts just keep chugging along. This state of non-deterministic chaos is called a partial failure, and honestly, it is the root of all our problems. So here's the crucial points. Our entire job as engineers working in this world is to just accept this reality. We have to build something dependable, something our users can actually trust, out of individual parts that we know for a fact are going to let us down, and in the most unpredictable ways imaginable. So where does all this chaos even begin? Well, it starts with the network itself, the very fabric that connects our system together, which, it turns out, is far, far less reliable than we'd like to think. The concept we're dealing with here is called an asynchronous network. And the best analogy? Just the regular old postal service. You can send a letter, but you have no real-time guarantee it'll get there, when it'll get there, or if the reply got lost on its way back to you. You're basically operating on hope. Now, what's so interesting about this slide is how it visualizes the client's total blindness. I mean, just look at these three scenarios. In A, the request gets lost. In B, the remote server is just down. And in C, the server did all the work, but the response got lost. From the client's point of view, all three are identical, just complete silence. You have no idea what actually went wrong. So the classic way we handle this silence is with a timeout. But this creates this terrible trade-off. If you set a short timeout, you might accidentally declare a slow but healthy node dead, and that can cause a whole cascade of new failures. But if you set a long timeout, your users are just stuck, staring at a loading spinner. From a senior perspective, this isn't just some technical knob to turn. It's a business decision that directly impacts user experience and system stability. There's just no single perfect answer. All right. Next, let's tackle an even more subtle and, frankly, mind-bending problem. Every single computer in your system has its own, slightly incorrect concept of what time it is. It's kind of like having two different watches on your wrist. The time of day clock is your normal watch. You try to keep it synced to the official time, but, it can get reset, it can jump backwards, or it can just be plain wrong. It can tell you the date, but you can't really trust it for measuring how long something took. Then you have the monotonic clock. Think of this one like a simple stopwatch. It only ever moves forward, which makes it perfect for timing things, like a request. But its absolute value is meaningless. It can't tell you if it's Tuesday or Saturday. And this right here, this brilliantly illustrates the danger. Okay, let's walk through this. Client A sets a value x to 1. A moment later, client B increments x to 2. But this happens on node 3, and its clock is just a few milliseconds behind node 1. Because of that tiny clock skew, the later write actually gets an earlier timestamp. So when the system tries to resolve the conflict using a last write wins strategy, it looks and thinks the write for x equals 1 is newer, and it completely throws away client B's update. This isn't a crash your users will report, it's silent data loss. Now, if we put on our senior engineer hat for a second, the problem is actually even worse than clock skew. Your application can be completely frozen in time for seconds or even longer by things like garbage collection, which is just an automatic memory cleanup process. When your app suddenly wakes up, it has no idea that any time has passed. Any assumption it made, like I still hold this lock or my security token is still valid, could now be dangerously, catastrophically wrong. So let's just take a step back. If you can't trust the network, and you definitely can't trust the clocks, how can any single computer in the system possibly know what's true? How is any decision ever made? Well, the system defines truth through democracy. It uses something called a quorum, which is really just a fancy word for a majority vote. A single node can be confused, it can be isolated, it can be paused, and it might be screaming, hey, I'm the leader. But if a majority of the other nodes have already declared it dead and elected a new leader, its opinion simply doesn't matter. The quorum, the majority, decides what is true. Okay, so this slide shows the classic disaster scenario. Client 1 gets a lock so it can safely write to storage. Then, bam, it gets hit by a long garbage collection pause. While it's frozen, its lock expires. Client 2 comes along, sees the lock is available, grabs it, and correctly writes its data. Then, Client 1 wakes up. It has no idea it was paused, it thinks it still holds the lock, and it goes ahead and writes its own data, completely corrupting whatever Client 2 just did. The solution to this is just incredibly elegant. It's called a fencing token. Now, when the lock service grants a lock, it also hands out a number that always goes up. So Client 2 gets the lock with, say, token 34. When our paused Client 1 finally wakes up and tries to write with its old, stale token of 33, the storage service itself just rejects the write. The storage service, the very thing being protected, becomes the enforcer of truth. It protects the system from a rogue zombie client. And from a senior engineer's viewpoint, this solution really highlights a critical principle. We talk about two properties, safety and liveness. Safety means nothing bad ever happens. That fencing token ensures we never, ever corrupt data. Liveness means something good eventually happens. The system eventually gets around to processing requests. When you're designing real-world systems, you can sometimes compromise on liveness. You know, it's okay to be slow sometimes, but you must always guarantee safety. So, what's the big takeaway from all of this? How do we even begin to approach building these systems with all this chaos in mind? Here's the final critical point, and it's so important. You don't achieve reliability by buying expensive, reliable hardware and just hoping for the best. You achieve it by assuming that everything, the network, the clocks, the nodes themselves, will fail. You have to embrace that pessimism and build the mechanisms to handle that failure directly into the software itself. And this leaves us with a final provocative thought. We've established that these problems of partial failure are deep, they're fundamental, they're unavoidable. So how is it even possible to build systems that we can actually trust with our most important data? Well, the answer lies in the beautiful and complex world of consensus algorithms. But that is a story for another explainer.